Hi everyone, welcome to this new episode of Join the Pod. It's going to be the last one this season because a lot of us marine mammal scientists going to be busy with fieldwork season, trying to make the best of the nice weather. Well, at least that's what we do over here in Ireland. Fiona is with us today. Cynthia apologized, she's finishing her PhD, so she was a bit busy. Fiona is with me, but her Teams is frozen, so I hope we can get her back soon. But so yeah, before we wish you all a nice summer, we have a super cool episode today with an amazing lineup of speakers who join us and will tell us about super fancy and useful sea robots, the gliders. So nowadays in marine research, it's really a tendency to try to develop more cost-efficient and less invasive methods that will allow us to survey the ocean remotely and over very large scale, like temporally and spatially. And gliders, they are really at the forefront of new monitoring tools, and they are very promising in marine science. And in marine mammal science, they start to be used more and more as well. And so today's speakers join us to tell us how glider can be used to carry out acoustic monitoring in the ocean, and who knows, also maybe detect marine mammals. So as usual, a bit of housekeeping before we start, and I hope it will let us give Fiona time to join us again. If you have questions, please post them in the chat, and then we will keep, there is some time planned aside at the end of the session so that the speakers can answer them. Don't be shy, we love any questions. I'm sure the speakers love too, and we'll be very happy to answer you. I'm just gonna double check the teams just in case we have. I'm gonna try to let Fiona in again. Sorry about this. Well, hopefully she can join us soon again. I think we can just get started and she will catch up. So, we have three amazing speakers joining us today. First, we will have Dr. Pierre Cauchy. He's an acoustician and an oceanographer and a glider enthusiast. His experience with glider comes from 10 years working with physical oceanographers. He has given the opportunity to attach acoustic recorders onto their gliders to develop new ways to observe the environment. He is now a professor in marine acoustics at the Institut des Sciences de la Mer de Rimouski in Canada, and he works and teaches many ways to use passive acoustics for ocean, marine life, ecosystems, and anthropic pressure monitoring. Next up, we will have Dr. Celine Frigosi. She's an underwater acoustician as well, and a sea glider pilot who is Ocean Associate contracted to the NOAA Pacific Island Fisheries Science Center Cetacean Research Program. She is also an affiliate researcher at Oregon State University, Cooperative Institute for Marine Ecosystem and Resources Studies. She received her PhD in wildlife science from Oregon State in 2020, where she focused on applications of passive acoustic gliders and deep water profiling floats for marine mammal passive acoustic monitoring and acoustic density estimation. She is currently piloting 2 sea gliders and in the main Hawaiian island, assessing the ability to conduct regular glider and monitor for false killer whale in the region. Someone who knows a lot about glider as well. And then last up, but not least, of course, we'll have Ellen White. She is currently a PhD student at the University of Southampton, and she works on automating the detection of marine sound sources from autonomous vehicles and large acoustic data sets. So she started out as a marine biologist at the University of Southampton. She has a passion for marine conservation and the management of our ocean, which drove her interest in marine acoustics. Her PhD works aim to develop useful algorithmic approaches for extracting ecological information from big acoustic data set to influence policy regarding marine protected areas and the activity that occurs within them. When she is not in the office working on saving the whales, she will usually be fun running, cycling, or swimming in the English South Coast, using most of her free time to explore the outdoors. Upon graduating her PhD, she hopes to pursue postdoctoral work and use her scientific background to influence marine policy within the UK and abroad. So as I was just saying, 3 great speakers today to tell us about gliders. We're going to start straight away with the first talk by Pierre. who's going to tell us about ocean gliders for acoustic observation, how to use them. I'll let you on the talk, try to get Fiona back, and hopefully, yeah, enjoy.
Hi everyone, thanks for offering me to join your pod. I'm happy to share my experience today regarding passive acoustic monitoring from gliders. Here's a few words about me. I was first an acoustician and I then became a glider enthusiast and an oceanographer. My PhD project was about adding acoustic sensors to oceanographic gliders to expand their observation range. Gliders are a powerful platform. They offer many observation opportunities. They also have a quite unusual behavior, and if you compare to ship or mooring observations, data processing might seem challenging. So I'm here to share my experience today on how to make the most of a PAM glider mission. I have collaborated with 2 glider groups. I've been given the opportunity to include hydrophones to a dozen glider missions. First in the Mediterranean Sea with the Moose Observatory, and then as a member of the UEA glider group in many missions across the world, as shown on this map. There was one constant to all these glider missions. It was that acoustic was not the main mission of the glider. I was a passenger to oceanographic missions, mainly long duration endurance missions, and I was also part of a few events where the capabilities of a fleet of gliders was being demonstrated. I worked with 2 different types of gliders out of 3 available at the moment. So this is a sea glider, and this one is a slocum glider. I've also used 2 different sensors. This is the Acoustic. It's a self-contained sensor. It's designed as a Mammal acoustic tag. So here you can see one attached on a sea glider and down there on a slocum. And here on your left is the first commercially available version of the sea glider integrated acoustic sensor. So why acoustic monitoring for gliders? Well, first of all, gliders are an amazing ocean observing platform. They are unmanned, which allows them to be sent to remote locations, deep places, dangerous places, near ice, under ice, in storms. That also makes them cheaper to operate. They offer a very long endurance. They can stay in the water for month to a year-long mission. They can cover about 1,000 kilometers in one mission, and they also collect hydrographic profiles, so they dive from the surface down to 1,000 meters, collecting hydrographic data. They have, in the past decades, they have proven their capabilities and their reliability as an operational platform, and they got much easy to use. They also offer a widening choice of payload, which is really calling for multidisciplinary observations, and that's where the idea of adding a PAM sensor to these came. What's specific about passive acoustics from glider? Mainly the silence. So the way gliders are moving through the water is very unique. It's called buoyancy driven, and that makes them very silent. So they don't have a propeller. They only rely on a bladder that they can inflate to float and compress so that they sink. And that way the glider will start from the surface here, then compress the bladder to sink, and they will dive down to 1,000 meters on this drawing here. Then when they reach the bottom, inflate the bladder again and go back up. And during these long and slow gliding phases, the glider is silent, and also the glider uses wings, fins, and just moves forward in any direction we want. So that makes them very good tools for passive acoustic monitoring, because no propeller noise and slow speed means low flow noise. Here is the recording, the spectrogram of a recording I've made during a glider dive. So this is here you have the surface phase right here, the glider goes down to the bottom phase is right here, and then goes back up to the surface again. This is a spectrogram. We have 4 hours of recording on the x-axis, and the y-axis shows frequencies. So low pitch sounds are here, high pitch sounds are out there. Yellow means loud, blue means quiet. So you can see there's lots of blue on this recording, which is a good sign. Now here are a few sounds you can still hear made by the gliders, and I want to tell you a bit more about these. Right, here you go. This was the altimeter of the glider. So when the glider is going down and approaching the bottom, you don't want to hit the bottom, so you turn the altimeter on to detect the bottom and trigger the transition so that the glider then goes back up. Here's the sound of the transition. So this is the glider inflating its bladder. It's coming soon now. Quite a loud sound. You don't want to be monitoring anything during this time. Then when the glider goes back up, here's another kind of sound you can hear during the gliding phase. So this is the glider slightly moving weights inside or its fin just to adjust its trajectory when going up. And when the glider is at surface, you can hear sounds of the waves basically splashing on the hull. Right, so these are the different phases of a glider's dive, and then the glider will reproduce this cycle over and over during the whole mission. I've extracted different phases. So you have the descent phase when the glider is gliding downwards, then the bottom inflection, noisy pumping, then the glider goes back up, quiet gliding, and then at the surface again where there is this surface noise. I've run some statistics on how long each phase is, and it turns out that on the glider deployments I've had access to, you are around 80% or more of the time spent just quietly gliding. So how do you reach such a good ratio, or how do you increase your ratio of quiet monitoring time? Well, it's all about the speed. You want slow dives because obviously you will glide for longer if it takes you more time to reach your depth. Go for deeper dive if you can. Same reason, it's purely geometric, but it will take you more time, so you'll have more gliding time again. And you can also limit the heading adjustments and the use of the altimeter to increase again your quiet moments. So these are tunings that are already or should already be done by any glider pilot regarding whether or not you're using an acoustic sensor, because it's saving energy. Gliding phases are not only quiet, they are also energy efficient. So you want to spend as much time as you can gliding to make your glider last longer. Another way to increase your time spent in these two green good condition phases is to reduce the surface time, and you can do this by limiting the amount of data you send back to shore. This has several effects. You save energy, you increase the safety of your glider by spending less time at the surface, you have less chances to be hit by a ship, and also you save on communication costs. Obviously, you send less data to shore, so you have less access to data in real time. Log files, all of the glider sounds I've presented earlier correspond to glider behaviors, and you can find information about these behaviors on your engineering log files. So if you look at bladder volume, battery position, pitch roll, and heading or bottom detection, they are all linked to one of these noisy behaviors I've seen before. So that's very useful. You don't need to try and detect these from your acoustic data. You can just read your log files and know when the glider is noisy, and then flag your samples, and that's done. Now, a quick word about flow noise. I said it was low. Here's two figures I've taken from a paper by Christine Erb. It's from comparing flow noise on a mooring to current speed, and what she shown was that flow noise is mostly limited to under 100 hertz, and also highly dependent on speed. So if you're on a glider and if you're interested in low frequency sounds, like Celine, our next speaker, in one of her previous papers. So she was after 20 hertz whale calls here. So we are definitely in the noisy area. And she noticed discrepancies in her flow noise between dives here in the red box and climbs in the green box. So as you can see on the spectrogram, you have more flow noise here when the glider goes down than here when the glider goes up, and this is directly linked to the speed of diving. So if you look at the white plot here, it's quite obvious that the glider is climbing up slowly and diving fast. So what you want to do as a pilot is to make this symmetrical. You want to be slow both ways to reduce flow noise and increase endurance. Quick numbers, usual numbers. So in the UEA glider group, the speed target you want is about 25 centimeter per second, which brings you here on this chart. As a comparison between flow noise you would be expecting from a mooring, well, out here in the Saint Laurent, you'd have currents from 0 up to 1 meter per second right here, and on Christine Erb's paper, she has had observations from up to 60 centimeter per second. So both these numbers are higher than the average or the target glider speed. And also one good thing is you can decide the speed your glider is going. You can't pilot the currents, you can pilot your glider speed. So regarding flow noise, gliders are obviously better than most moorings. And as far as I know, drifters would be the only platform that is better than a glider, because it's obviously drifting with the water, so you have absolutely no flow around your sensor. And by the way, gliders can drift, so that's a new behavior for at least some gliders. You can ask them to stop moving and drift at depth, so if you want to really get rid of flow noise. Sampling now. As I say, gliders have a unusual behavior. Here is the mission plan for the ACOBAM survey initiative. It's shipborne observations, either visual or acoustic, and it's providing a snapshot of the marine mammal population in the Mediterranean Sea. The whole plan is based on a regular pattern with no overlap and high speed of the ship regarding the swimming speed of the species you're after. This is because you want to achieve synoptic observations. So synoptic observations are simultaneous observations from different places, either actually simultaneous, or in this case you assume that it can be assumed as simultaneous because you're moving much faster than your target species. This is obviously not the case when you use a glider, so you have to adapt the way you sample. So gliders are not fast enough to provide synoptic observations on an ocean basin, but if you focus on a smaller scale, they are very good at repeated observations at a high time and space resolution. So here are 3 usual patterns used by oceanographers using gliders, and they are adapted to oceanographic features they want to observe. First of all, if there is no specific features you're after, then the virtual mooring pattern provides time series of observations at a high resolution. So you just ask your glider to stay around a waypoint, and the glider will perform successive dives at the same time and at the same place, and provide you a nice time series to analyze. Then if you have a one-dimensional feature such as a front or a slope, then just repeated sections in and out will provide great data on either on this feature or on what's happening on both sides of the front. And for a two-dimensional feature such as oceanographic eddies or seamounts, then you can use the butterfly pattern, which will do the same basically as the repeated section, but in 2 dimensions. Now here's my summary about this. First of all, be slow. You will reduce flow noise and increase glider endurance, which is a win-win. Then keep it simple. It is exciting to be able to send your glider anywhere, but does it need to move? Just keep in mind that simple trajectories, simple patterns make for much easier analysis. Use the oceanographic observation. It's always good to link whale presence to water masses, and also you can use oceanographic observations and target oceanographic features for your observation, because it will probably give you more exciting observations. Finally, it's not hard, so adding a hydrophone on a glider is not too much work and brings lots of opportunities for multidisciplinary use of your mission. Right, and looking forward to answer to your questions now.
Thank you very much, Pierre, for your super interesting and comprehensive talk. I think now we all have the keys to start planning successful glider missions. I've been taking notes, and I will surely use your advice for the next one, that's for sure. And so, yeah, I think now that we know more about gliders and how to correctly use them, I think we can learn more about the way they can be used to monitor cetaceans with Celine and Ellen. And so we're going to start right now with the talk by Selene, which is going to tell us how to use passive acoustics to listen for whales specifically.
Hello, thanks for joining and listening into my talk. I'm going to be talking about how we can use passive acoustic gliders to listen for and study whales. So quick outline, I'm going to touch briefly on the motivation for using gliders to record and survey for marine mammals. I'll go through 2 example experiments where we compared glider-collected acoustic data to more traditional stationary recorders, and then give some examples of what is next with passive acoustic gliders and whales. Traditionally, studying marine mammals was done visually, but whales are hard to see. They spend most of their lives underwater. Conversely, all cetacean species regularly produce species-specific vocalizations that they use for foraging, navigation, communication, lots of life functions. And so we can listen passively to these sounds and actually use that to study marine mammals. There are 2 types of acoustic recorders that have been traditionally used for passive acoustic monitoring of cetaceans. Probably the most widely used recorder type is stationary recorders. These are really quiet. They can be deployed for weeks to months to years, and they provide really great temporal coverage because they're out for so long. They sit on the seafloor or are attached to moorings in the water column. And so here is a picture of a stationary recorder being lowered into the water off of the back of a ship. But stationary recorders have limited spatial coverage. They sit and monitor in just one relatively small area. So for example, over here with this map of the Southern California Bight, if you've got 3 recorders out at these stars, these purple circles might be the total area that you're able to monitor. At the opposite end of the spectrum, we have ship-towed recorders. These are great because they can survey across oceanographic features. You could pair visual observations with the acoustic recordings to pair up species ID or observe animal behavior associated with certain vocalizations. And so this teal line over here shows how you might be able to survey this whole region in one trip. But ship-based surveys are typically short duration. They can last only a couple weeks. They can only take place during seasons and in weather conditions when it's safe to go out on the water. And additionally, animal behavior could be altered by vessel presence, the vessel itself generates some low frequency noise that may mask signals of interest, so they have their limitations. But today's webinar is all about gliders. So on to the gliders. More recently, mobile autonomous platforms, such as autonomous gliders, have been used to listen for marine mammals. This term, mobile autonomous platforms, encompasses a whole range of low-power, long-duration instruments that move slowly relative to a ship's speed, and they're considered relatively quiet because they have limited moving parts. But the main advantage is that they address the spatiotemporal trade-off between stationary recorders are long duration but small spatial coverage, ship-towed recorders are good spatial coverage but short duration. So gliders sort of fit in the middle and fill an intermediate space between those two. So several types of gliders have been used to survey for a variety of marine mammals around the world over the last decade or so. But these systems are really dynamic. They're still relatively new. So they move both horizontally and vertically, and moving parts may generate additional sources of noise. Basically, there's still a lot of questions about how we can best use these platforms to answer important questions in marine mammal science. So for this webinar, I wanted to present the results of 2 case studies from my dissertation research that tried to answer one of the more basic questions about glider use. How do they compare to stationary recorders? So for if we want to start using gliders more regularly to acoustically survey for marine mammals, and ideally be able to compare any results that we're collecting with gliders to historical results, we need to understand how data collected by a glider might differ from data collected by stationary recorders. Are we comparing apples to apples or apples to oranges? Are we able to hear over the same distance? Are there introduced noises or biases that we need to account for? Which type of recording platform is best for which species, which area, or what kind of research question? To look at this, we did 2 experiments in 2 deep ocean basins in the Southern California Bight, and we tried to tackle this question for 2 species that produce drastically different vocalization types. So one, the fin whales that produce very loud, omnidirectional, low-frequency calls for hours at a time. And then on the other end of that, beaked whales, which produce very high-frequency, highly directional echolocation clicks that can only be detected over a few kilometers, and they only make these sounds when they're diving to extreme depths to forage. So first, fin whales. This plot here shows a spectrogram or visual representation of the sound produced by a fin whale. So the frequency or pitch is on the y-axis and time is on the x-axis, and these red bits right here are the fin whale 20 Hz call. It's produced by males in the winter in long bouts called song. They're really low frequency and can be detected over tens of kilometers. Again, we recorded on a stationary hydrophone, on an array of stationary hydrophones and a glider in the same region for the same exact 2 weeks. We then used an automated call detector and quantified call presence or absence in hourly and daily bins, as well as the rates of call detections per hour. And so the scale of daily or hourly presence, meaning at least 1 call was detected in that hour or day, which is a typical reporting scale for something like baleen whale song, the stationary recorder and glider performed the same. But the actual number of detections per hour was only half as much on the glider. So what was going on? This figure, again, shows a visual representation of the sound, but now it's over 24 hours. The dark blue is quieter and the light blue is louder to yellow. These black bars are when the glider was not recording, when it was at the surface, and then this white line shows the glider's dive profile up and down in the water. So you can see here, these little specks, these little lines at 20 Hz are the fin whale calls, but you can also see these sort of solid, brighter areas. This is flow noise recorded on the glider. So the glider descended faster than it ascended. So this portion here is the descent, and then this portion here is the ascent, because of how it was ballasted and the local oceanographic conditions. And so when the glider was moving at these higher speeds, the low frequency flow noise was generated and it masked those fin whale calls. And this plot here just shows it in another way. This black line is the moving average of the detections per hour on the stationary recorders. And then these red triangles are the detections per hour by the glider, and I did the moving average here for just the descending portion of the dives, or the ascending portion. And you can see the ascending portion actually follows the stationary recorders pretty well, but the descents have really low levels of detection. So to summarize, detection rates were the same at daily and hourly scales across both recorder types, but flow noise on the glider reduced the number of detections per hour, which highlights the key to a well-ballasted glider for this sort of experiment and detailed assessment of background noise variability during a survey. And we found that ideally a sea glider would be flown at speeds through water of less than 30 centimeters per second to avoid this low frequency flow noise that masked fin whale calls. So next we did a similar 2-week experiment, but this time we were looking for a different sound type, the echolocation clicks from Cuvier's beaked whales. These clicks are highly directional, sort of like a flashlight beam directed into the dark, and are used by Cuvier's beaked whales to forage for squid. They're much higher frequency than the fin whale calls, far above our hearing range, and so they don't travel nearly as far underwater. They're detectable only over a few kilometers at the most. So for this experiment, we manually identified beaked whale echolocation clicks in the acoustic record. We quantified the clicks at daily, hourly, by minute bins, and then also the total number of encounters or sort of bouts of clicks all grouped together that were recorded by each platform. What we found was that the beaked whale encounters were relatively scarce in the region at this time of year. This plot here, this map is just really zoomed in, shows the glider track in orange, and then the circles are the location of the glider when it detected clicks. The glider did have marginally more encounters and greater presence at all of the different bin scales compared to either of the 2 stationary recorders. Further paired encounters, so instances where clicks were detected on 2 recorders at the same time, were really rare. We only had a single instance where clicks were detected simultaneously on the glider and both stationary recorders. It's shown here with this black star. And even more interesting, I think, is that even when the glider and the stationary recorders were within a kilometer of each other, it didn't necessarily guarantee that both instruments would record the same set of clicks. So to summarize that experiment, the direct comparisons are really challenging for the kinds of sounds produced by beaked whales. The spatial overlap of the recorders was really important. The detection rates seemed more highly dependent on the survey location, like where the platform was, rather than anything about the platform itself, like its noise profile or its depth. And basically, you had to be in the right place at the right time to get something like beaked whale clicks. And this may indicate that platforms that can move and survey across complex bathymetric features might be particularly useful for identifying hot spots for species like beaked whales. So what does all this mean for the future of marine mammal research and conservation, besides, that gliders are kind of a fun, cool, exciting new tool? What can we do next with acoustic gliders? Density estimation. This is something I'm really excited about, and work is ongoing. So we know we can count marine mammals by counting their sounds. We can do some math and then get to the total number of animals from the number of sounds we record. And we can do it with gliders. I think we can. We're still working on it. It's not all worked out yet, and it's really complicated. But this is really exciting ongoing work that's happening right now. Another exciting frontier is real-time data reporting. So the glider surface and call a base station on land every couple of hours. Work has already been done to automatically detect and report baleen whale call presence on the east coast of the US and Canada. But this hasn't been done yet with odontocetes or toothed whales. So I'm currently working on a project with collaborators in Hawaii and at Oregon State University to develop a real-time detection system for endangered false killer whales in Hawaii. We've got 2 gliders out right now, and this map is just from this morning showing their track along their survey region. Another thing is that gliders can go where no recorder has gone before. We've already seen this in practice. Gliders can survey areas that have been traditionally undersurveyed due to resources or weather, distance from a reasonable port, that kind of thing. So for example, the gliders helped identify a new marine mammal sound that it recorded near the Mariana Trench, a notoriously difficult area to study by ship. So that was, this spectrogram here shows this really crazy awesome sound called the biotwang that was identified from glider data. And then a few years later, a ship-based survey went out and was able to confirm with visual sightings and acoustic recordings that this call is produced by the Brutus whale. And then lastly, gliders are collecting very fine-scale environmental data at the same time as it's collecting these acoustic recordings. And so the use of integrating this oceanographic data with the acoustic recordings to try and look at habitat use and contrast the animal presence with these environmental variables seems like a really promising new research area. With that, thank you very much, and I look forward to the discussion.
Thank you, Celine. Once again, very interesting talk. It's quite impressive, the amount of data you could collect from the gliders. It seems very promising as well, like especially for the rare species like big whale, where it's very difficult to detect them during short vessel surveys, but getting the spatial coverage with a static, as you mentioned, is not the easiest either. So no, it's very super cool, and knowing how it compares between techniques is really useful. And yeah, when you mentioned all the what's coming next for the glider, seems like there's so many things that are going to happen. Like maybe one day we'll get real detection of marine mammals a bit everywhere. That would be very, very cool. So just to finish up for today, we're gonna jump into with Ellen. She's gonna talk a bit more about the application of glider-based acoustics. So other examples of how to use them for marine mammals. And I think she's going to tell us a bit about how to identify and classify different sound sources collected from glider, including stations. Yeah, enjoy the talk.
Good afternoon. Thank you so much for coming to the webinar. I'm going to talk to you a little bit more about AUVs and gliders that hopefully not overlap too much with what you've just heard. So I'm Ellen White. I'm a PhD student from the University of Southampton. And my PhD is looking at how do we automatically detect signals in marine data sets, specifically looking at marine mammals and anthropogenic sound sources. And the future work is sort of extended to how do we deploy that kind of algorithm onto a glider or another form of autonomous vehicle. So I'm going to talk a little bit just about an overview of kind of some of the things I look at and work on and some of the issues around using these kind of platforms. And hopefully it'll be interesting to anybody who's wanting to use gliders, and also just interesting in case you get hold of a data set with gliders and aren't sure where to start. So if you have any questions or you want to follow up on anything, please feel free to email me. And I just want to give a little shout out to anyone who sponsored or funded this work or has collaborated with data sets, etc. So in terms of marine data, when we record passive acoustic data in the oceans, we record a plethora of sounds, and those come from natural sources as well as anthropogenic. And for the region that you're specifically monitoring, any of the sounds present, when you add them all up together, it creates a soundscape. And so a more typical approach to sometimes automatically detecting specific pieces of information is to think of a species that you're interested in. So for example, dolphins, they whistle. So maybe you'd want to build an algorithm that looks at, can I detect whether or not a dolphin is whistling in the environment from a ship or from a glider? But my work sort of, it goes a little bit beyond the binary, is there a dolphin or no? And it looks at what kind of sound sources are present. And the idea behind this is that when you know the different components of a soundscape, you can infer ecological information, and you can actually sort of get an indication of the health of an area based on who's making what sound and what's there. And my future goal is also to sort of be able to maybe give a little bit more ecological context to what's happening in the acoustic data. So say you have a lot of dolphin activity in one area, and then all of a sudden you get a lot of vessel activity and the dolphins leave, rather than just having a dolphin presence and absence detector. Now that the dolphins are absent, the same model could be able to tell you, well, there was a ship there and maybe they didn't like the noise. So you can start to build up a little bit of an ecological picture. So that's kind of the overall theme of my work, and the bigger aspect then is how do I get this to work on a glider? And so some of the things you have to think about are, what do these sounds sound like from different platforms? So the marine soundscape, as I said, lots of different components as we've talked about, and when you want to deploy a glider or something to record all of these, you have to bear in mind all of these sounds, they overlap in terms of their frequencies. That's how we talk about and describe sound sources in the marine environment. And so a dolphin can overlap with a fish or a humpback whale. Sometimes a vessel, if it's too close to the hydrophone, can mask all of the biological sounds. You get lots of rain and wind in Scotland, where I work specifically. So we call that geophonic noise, and that adds a lot to the soundscape in terms of how loud the ambient noise is. So the ambient noise would be noise in absence of the signal that you're interested in. And so collecting all of these sounds is really important, as I said, for ecologically understanding your environment, but it also makes it quite a difficult task. And then, as I'm going to talk about in a little bit, it gets even more complicated when your vehicle, well, for a starter, when it's a vehicle in the first place and not just a static point of interest that you're recording. What happens when the vehicle is moving as the sound's being made? And how do you go about trying to use that? And I'll give you a little spoiler here. I don't have the answer to that yet, but my work is moving towards sort of understanding that phenomena a little bit more, especially in shallow water. So ocean robotics, which is what we're here to talk about today, as I'm sure you've heard a lot about by now, are marine vessels that are autonomous in nature and they survey the ocean. They're typically a much more sustainable option because you don't need to send a ship to sea, so that's really optimistic for us. And the other thing that really intrigues me is that they go into so many different environments and they can survey for such different times, and they're up and down in different soundscapes over time. The data that they collect is so different to what we're used to on a static array. They can go for really long periods of time or short, depending on the nature that your survey is going for. There's lots of different choice that you can have. The top two vessels I can show you are surface vehicles. So they sit on top of the waves, and you typically would have your hydrophone hanging below. And so that's going to give you a really different data type than if you had a static array on the seafloor, or if you had a glider that's traversing the ocean body in the center of the water column. So all of those are really interesting factors to weigh up in what kind of vehicle you collect. And that's a really niche question, depending on your application. But mostly the work that I do is on gliders and on surface vehicles. So that's what we're going to talk about today. But these vessels are opening up a wealth of PAM data that we can collect on scales that are even bigger than what we've collected before. And so anybody who works in this field is going to know that this bottlenecking concept in bioacoustics is quite limiting, because we're getting all this data on all these different timescales, but how do we pull something out of that data? And that's sort of the area that I'm interested in. So as I said, I'm interested in how do we detect sound in these big data sets. So the key question is, what's in the data, and how useful is this to marine management and stakeholders who are planning maybe marine protected areas, or scoping out a site for a new development or some kind, and we need to know what's in the water column and where. So when you have a static array, you have a very fixed point in the ocean body, so you can model how the acoustics are going to move around your hydrophone, and then you can look at what your probability of detection is going to be. And then from there, you basically build some sort of detector based on the column that you're interested in or the frequency type. So some of these spectrograms are examples of different sounds that maybe you want to pull out of the water column. And you're basically wanting to develop a model that can say, is there a species, yes or no? Is there a vessel, yes or no, depending on your question. If you're really lucky and you live somewhere where there's a lot of annotated data and species information out there, you could probably even say which specific species is this, as opposed to just a dolphin or a porpoise. In the UK, we're not quite there yet, but we're getting there. So this is where I sort of come in, and I'm not going to talk to you today about automated detection mechanism, algorithms or anything, but I just wanted to give a bit of context as to why I'm interested in using these platforms. So I would like to have a system that you can put data into, take it off the platform, and it'll tell you what's in it in an ideal world, but that's quite a big goal. So for my work, I'm working in the west of Scotland with the Compass project, run up at SAMS in Oban. So we have 12 long-term monitoring static arrays, and they're monitoring for marine mammals year-round and collecting lots and lots of data over time. And these marine protected areas are typically there for dolphins and porpoises, so that's the species that I'm interested in. And so you have these kind of high frequency species present in terms of their acoustic behavior in an area which also has quite a lot of anthropogenic activity, because we have a lot of ferries to and from islands, there's a lot of fishing activity, acoustics terror devices are rife. So all of that is kind of going on in this area, and we are monitoring it from 12 static points and comparing them or data across the sites. But the acoustic variation in locations like this is really interesting, and each of these individual moorings is going to have a completely different behavior in terms of acoustic propagation of the sound sources. And so having a moving platform that could go between them would allow us to monitor a much greater area of these marine protected sites and non-protected. But it's also going to mean that we're introducing a vehicle to a very disturbant acoustic environment. And how do we understand the data then that we're collecting is the question that I'm sort of looking at. So as I said, I work on the continental shelf, and this is typically between 0 and 200 meters depth. So it's a really interesting acoustic environment to deploy a glider or a surface vehicle into, because in acoustic or in shallow waters, the acoustic nature of sound sources is that it gets very lossy. So when you send the sound source out, as it travels through the water body, depending on the weather, the temperature, the salinity, the oceanography that's going on, it's very unpredictable how that sound source is going to travel, depending on the sound speed of the area. And sound speed is directly affected by temperature and salinity. So if you have a stormy period and we've got a really mixed water body, you might have a very constant sound speed. Whereas if you have very calm weather over time and it's a nice environment, you might get quite a stratified sound speed profile. And so how the sounds that you're interested in propagate over the area is going to change. And your detection probability for your glider that you're interested in is also therefore going to change. And if you want to So in terms of where am I going with this, basically? So as I said, it's very difficult to predict this acoustic behavior, and we could talk for days about acoustic propagation in shallow waters. It's a very big field. But what's important to take away here is the vehicles that we're now using are traveling at different depths in the water column. So these AUVs, typically gliders, we're seeing more and more coastal gliders coming out, and they can traverse the water column from 0 down to 200 meters and back up again. And obviously in the open ocean, they do that a lot deeper. And when you have a static array, it's at a fixed depth. So the water around it is continuous, even if it's getting mixed. That water isn't going to change around the hydrophone as such. Obviously it will change with the parameters, but the mooring's not moving, whereas your glider is having to move through different oceanographic changes while it's recording this passive acoustic data. And then you have surface vehicles, which are right up at the surface of the water. You're going to get splashing from the vehicle itself. You're going to get quite churned up in the upper surface level of the ocean, because the sound it's a lot of where the sound is refracted and lost. So it becomes a very noisy environment up there. You get a lot of cavitation and bubbles. And yeah, it's a very noisy area of the ocean to be in. So when you're trying to see if you can detect and automate the process of detecting marine mammals, you can see how this becomes increasingly a very difficult question. And gliders are quite a new phenomenon. So we typically don't have that much historical data for them. So when you're building a classifier or a detection algorithm, you need exemplar data from the platform you're going to be using, which is very limited for these new technologies. But we do have static array monitoring data. And so that gives us quite a nice comparison site to start answering these questions. How does this data vary depending on where you collect it? And how do the species that I'm interested in, how do those calls get affected? Because as you said, dolphins, very high frequency sounds don't travel as far in water as they do in air, or as low frequency sounds do. And so with these marine protected areas, and you have dolphins and porpoises are calling it over 100 kilohertz. Dolphins are maybe from 2 up to 50 kilohertz, and some even higher. So the range of detection is quite small anyway. And then on top of that, you have a very good phenomenon where if you aren't heading in the right direction towards the animal, or you're just off axis from where the animal is making the sound, you might not be able to detect it in the same way as if it was facing towards you. So there's loads of different things to think about in interpreting your data. So how am I actually going about trying to understand any of this is where we're kind of going. So comparing platforms is the key part of this work. So we've, alongside with Saish and Audinal, and in future we're going to be doing some glider work here. We basically have taken two moorings, which is Stanton Banks and Garvalax, from the Compass project that I was speaking about earlier. And there's another mooring that Sounds also operate just a little bit further off the coast, almost off the continental shelf at the Rockall edge, but not quite off. It is just a little bit deeper. And so we have these three static arrays that are monitoring year-round collecting data. And so the figure on the left here is showing you where there's a blue line. These are tracks that we were able to sail the Audinaut surface vehicle in the west of Scotland and record passive acoustic data. And so we're now going to try and, first of all, model the acoustic propagation qualities based on the weather at the time of the survey, and then compare and contrast from the static array raw data to the Audinaut raw data. What levels of species detection are we getting for dolphins and porpoises? And how are these rates affected by the parameters that affect the acoustic modeling? So that's kind of the big scope of the project. And then on top of that, on the acoustic mooring buoys, we also have what's called a C-pod. So C-pods, if you're not familiar, are click detection automated systems that you can put next to your hydrophone. So it doesn't store any acoustic data, but it does tell you when it heard a click for both dolphins and porpoises and even sperm whales, which we do occasionally get in this area. So we are going to run click detectors on our Audinaut data and compare it to the C-pod data as well. So this is kind of a overview study of how does static array compare to an autonomous vehicle, and then how does raw data compare to the C-pod detector in terms of automated detection algorithms. And hopefully we're sort of building up a picture towards suggestions to the scientific community on how to operate these kind of studies in coastal areas. So I just wanted to give you a little bit of preliminary data to show you. So this work was carried out, this is some of my colleague from Saish, Lorenzo, has been looking at the detection rates on the Audinaut vehicle itself. And I'm sort of working on the comparison end. So we're getting really nice detections here. This figure is kind of showing you where the different moorings are, as well as dolphin whistle and dolphin click detections in the left-hand panels, and then porpoise detections in the right-hand panel. And so we're sort of seeing, first off, as an interesting point, is a lot of our detections that we're seeing on the Audinaut are actually not in the areas that the static moorings would cover. So that's really interesting because we're using these moorings for marine protected areas, and already the moving vehicle is showing us so many more detections just outside of that detection radius of the static array. And on top of that, we're getting a lot of whistle and click detections in the same track line, and so that gives us quite a good baseline to start looking at how we might work out density estimations, etc., from this kind of data from the surface. And so my job, as I said, is to compare this to the static array, which I'm not going to display today because it's not finalized yet, but it is proving to be quite an interesting study for a few reasons. So when you're looking at the AUV data, it's really important. This goes for gliders as well. This isn't just Audinaut, but it's really important to think about the self noise. So if you're running the data through an automated detector, what kind of self noise from the platform is going to flag up as a false positive? What was the environmental noise, and how is that affecting what you're detecting? Is there any electronic noise? So in the spectrograms you can see on the right-hand side, there's a lot of vertical or horizontal lines displaying in the visual image, and those are all electronic pieces of noise coming out of the platform. And this is just a really common phenomena in gliders and different kinds of vehicles like this. Of course, if you're looking at a really narrow frequency range, this isn't as much of a problem because you can kind of just zoom in and narrow this down quite nicely. But because I'm looking at the soundscape, this poses quite a problem. So now we're looking at How do you denoise this kind of data, etc., etc. And so these are all questions that we need to answer before I can look at comparing it directly to the static array. It's not quite as simple as just saying, oh, we heard 8 dolphins on one platform and 9 on the other. Really understanding the acoustic environment and getting into the nitty-gritty of the acoustics itself is how we're going to start to understand what these platforms' benefit is. Just to highlight one of the things that's also really interesting is the self-noise platform of the vehicle, because a lot of times these vehicles are sold as really silent, and this figure basically shows in the black line is a static array frequency domain plot of how loud the platform is over time. And then the red line is one of the autonomous vessels. So you can kind of see, although we get a lot of different spikes in activity in the autonomous vessel as a result of self-noise and electronic noise, it does give a very similar noise profile. And so that's pretty optimistic to know that the soundscape overall is quite similar in terms of what we're surveying. But this is a preliminary piece of work, and we're seeing different phenomena in different regions that need to be researched a lot closer. So finally, how do we move towards automating this? So these platforms are giving us a lot of data, and this is a really good example of a wide range soundscape spectrogram from these platforms. So you can see there's a lot of electronic self-noise, which is where you get these really straight horizontal bandings. They're very difficult to filter on because they're not streamlined in nature and they vary. And they also occupy frequency bands of the key species of interest. So typically for dolphins and harper porpoise, a lot of the energy is here. And then on top of that, you get these kind of really loud occurrences of geophonic noise as a result of the vessel being at the surface or as the glider comes up to the surface. So there's a lot of different components of the soundscape of a glider that aren't prevalent in a static mooring. And that's something really important to think about when you're looking at automating pipelines and how do we create these algorithms. So one way to go would be to basically just run loads of experiments, get loads of data and train models on data from every single platform, but that's just going to take so much time and it's not really useful. So I'm currently looking into different denoising methods for these data types, really trying to understand how the different data types relate to one another in terms of their statistical diversity. So looking at ambient noise levels across the platforms at different times and seeing how the data distributions change, which is becoming a really interesting piece of my work actually. And then just really understanding the local oceanography around the vessels and vehicle types compared to the traditional methods of survey, and understanding what that environment is going to be that we're putting this vehicle into. So thank you so much for listening. I realize this is quite a broad overview of some of my work, and it's maybe a little bit more applied than the general approach to waterborne gliders, but I thought it would be cool to show you what this sort of theory behind how you interpret the data from a glider would be. And the sort of scope for this work going forward is that if we can work out robustly how to compare data across static arrays and AUVs, both within the water column and at the surface, in such turbulent coastal shallow waters, things like marine protected area management could be done autonomously with autonomous vessels, which is a much more sustainable option for marine science in general. And I think that's sort of the way we should be heading. And then obviously the goal for most people in my field of detection and classification is eventually to be able to detect these kind of sound sources in real time. But hopefully from my talk today, you can see that that's becoming quite a difficult, ever complicated feat to begin with. So thank you so much for listening, and I look forward to a discussion after the seminar.
Hey, thank you, Ellen. That was a very nice way of wrapping things up, I think. It was good to have an example of a surface glider, actually, because we didn't hear about them yet. And yeah, I think it's nice as well that you mentioned that besides improving the way we use the gliders, them like itself, like in like the practicalities and the logistics, there's also still a lot of work to do with like the way we analyze the data, so the computer side of things and how we treat all these acoustic data we're using and make sure that we're actually analyzing like properly. Yeah, so thank you very much to the three of you. Like the three talks were, I really liked them. I don't think we had questions, but this happened before, so don't worry. Like I'm sure we have questions for you. If you have questions for each other as well, just don't hesitate at all. I'm sure we can like learn a lot. And Yeah, I don't know if you know if no, there was no question in the live. No, I didn't check, but no.
No, there was no questions.
Okay.
But I have a few questions.
Nice. Sure. I'll go ahead then. I have some as well, but.
Yeah, that was really interesting because I don't know much about gliders at all. Where Morgan, I think you have some experience with them. So it was a really good introduction to me for how they work, like logistically, and pros and cons, and what needs to be, I don't know, changed going forward, and all of these things. And how it fits in with more traditional methods. And, you know, sometimes you hear about these autonomous things and you think, oh, they're going to take over, don't even need to be out in the field anymore. Yeah, we're not there yet. Which is actually one of my questions. Do you think in the future, at some point, there will be a time where almost everything is autonomous and we barely need to go out in the distant future? That's kind of a general question, I suppose, for everybody.
Well, no. Well, you still need to deploy and recover the gliders. We had a plan at the UEA, Karen Haywood's group. She's working on using an autonomous surface vehicle to deploy a glider for them. So you can imagine to have less and less things to do. But nah, we'll always be needed somewhere to fix things and recover. No worries. There will still be fieldwork opportunities for you all.
Yeah, I was going to say the same thing. Like there's too many other questions that can't necessarily just be answered with passive acoustics too. And I think that's kind of one of the really cool things about gliders is that they're enabling us to, we're finding little bits out and then they sort of complement traditional methods really well. So like with this unique sound we recorded in the Mariana Trench, the glider didn't tell us anything about what species it was. It was just the sound, and we could kind of deduce that it was more than likely biological, but people had to go out on a ship and get visual confirmation, get biopsy samples. So I think, you know, removing that side of things won't be happening anytime soon, just really depending on, there's too many other research questions that I don't think we can necessarily answer with acoustics. But in terms of surveying long durations, broad areas for management, I think, and long time series, then I think that's sort of where these guys shine.
Yeah, I feel like Celine really summed it up well. But yeah, I was just thinking there's too many. I'm sort of, I guess, biased to my own work, but even things like machine learning in terms of labeling data. I mean, if we're just sending gliders out with no visual ground truthing confirmation, we're never going to get any closer to trying to figure out which species is making which call. I work a lot with delphinids, and they're just a nightmare because it's so difficult to correlate their calls to species type. So if anything, I think at the minute we need more ship surveys where people are actually going out and seeing them. As much as this autonomy is going to be, you know, fantastic, there's way too many more questions, I think, to answer.
That's good for everyone, I suppose. Still work for a lot of people. You know, it's very nice. I had a more technical question, maybe, I don't know. So if I understood well, Pierre, in your presentation, you were saying that the most silent phases are the descent and ascent, and then you, Ellen, were talking about the shelf waters. And I know a lot of studies that use gliders, they make the most of the capabilities of the gliders that can dive very deep. But so I was wondering, like, if you were going to work on quite shallow waters, is it worth it to like make the glider dive very often, or would then maybe a surface glider be more appropriate? Because then the surface is also a bit more noisy. So I was wondering, because I'm working as well with the glider on the shelf, like in the same area than Ellen, really. And I was like, is it going to dive too often? Then would it be worth it? Or should I just like do longer? I don't know. Do you have any inputs on using them in shallow waters? Is it as interesting?
Yeah, well, so from my perspective, I guess there's two answers. The first one would be there's quite exciting new coastal gliders being developed. I haven't actually seen anyone paper-wise publishing using them, but it is a huge new area of opportunity. I went to Ocean Business, the conference, and I got to see some really cool coastal gliders in action. And yeah, they have fantastic capabilities, and just the way they operate is quite different, and they sort of go on much more gradual descents and ascents. So they're really making use of sort of what the oceanography is doing and making sure you're not just constantly going up to the surface and causing lots of noise. So I personally, this is why I ended up using the surface vehicle, because deploying the glider in that area of West Scotland was so tricky because of shallow water. Even just the company I was working with, they didn't want to risk their glider crashing because it was so shallow. So I don't have a huge amount of advice on how to design the survey. I feel like Pierre might be better in shallow waters, but definitely keep your eyes peeled for coastal gliders because it is a big thing.
Yeah, well, I'm not sure how shallow waters you're speaking of. We've been using shallow slocum gliders. There have been 200-meter versions for years now, for as long as I'm in the field, actually. They work well in, say, below 50 meters. They will work well. They have faster pumps than the deep gliders, so the pumping phase lasts for shorter. And yeah, they'll be more designed to have a different angle, so they will still manage to be slow under the water and to glide for long enough. But yeah, I didn't mention this, but I've worked mostly with deep gliders. I've compared this 40% ratio to a few shallow glider missions where the glider was only going to 200 or 300 meters, and clearly there's a difference. You still have a solid 50% of your time where the glider is not making noise, so still all right. I think then there's I mean, if 50% is enough, it's still all right. You have ways to maybe turn your sensor off when the glider is making noise, so you're saving energy. You will be having only 50% of your time, but for longer duration, so it's still worth it. Then I've never really tried these surface vehicles. I think they come with more noise and more complications. You need a towed array, so you want to have your hydrophones away from your hull because the waves will be making noise on them. And these all these flapping propulsion systems, even if it's not a propeller, there's I can see quite a few sources of noise on these things. So yeah, clearly. Gliders will be more silent, but these surface vehicles will work in so much shallower waters. They're not doing the same thing. I think that's the main message here.
And I suppose it's true, like even if it's only 50% of the time that is like more silent compared to a vessel survey that you would use for spatial data normally, it can still be much more silent than the vessel engine. I suppose it depends what ship you're using, but sometimes, like I've been doing PAM surveys on vessels that are quite noisy, and in the end, like, it masks a lot of the signals. Well, that's very nice.
Pocket gliders, like they would be very small, and these ones I've seen videos of demonstration like make-believe gliders that work in a swimming pool. So if these actually work and carry a hydrophone, that's the solution for your shallow waters, clearly.
Yeah, that's very nice. I will be really looking forward to see what's going to come out in the next few years. It's growing very fast, I have the impression, like all this field of the robotics, and when everyone works together, big progress in terms of development of equipment. I had other questions, that's for sure. I'm trying to remember because I was listening to the talks and I was like, yes, you mentioned, a few of you, how the property of the ocean affect the way noise propagates, of course. And I was wondering, depending on the area you're monitoring, like would you, for example, Selene, when you detect the beaked whales or the fin whales, would you try to correct for kind of this, like if your glider suddenly enters an area with like the temperature is different or something, would you still plot the detection like kind of where you had it, or do you think it's worth trying to take into consideration in the marine mammal data that the detection function was varying or something like this. I think it must be very complicated to do, maybe. Like, I wouldn't know how to do that. Just asking.
Yeah, no, that's a really good point, and it's something we like have talked about but have not done yet. So I think there's kind of a reason that it would matter and maybe be useful, but it depends on sort of what your question is. So the stuff I presented today was more about just like whether like presence or absence. And we did go into a little bit of trying to model sort of how the detection range specifically for fin whales varied, like depending on the glider's speed. So as it masked, it like shrunk the little circle we were listening. And then as the glider was going slower on the ascent, we were likely detecting over much larger ranges, but that we did that like very simply with like a 20 log R assumed spreading loss. So we haven't done any detailed propagation modeling about how that detection range is varying based on the depth, and kind of like what Ellen, you were kind of touching on that, how it's moving through these different parameters. That's a question like I've gotten lots of times at talks, and we haven't done anything with it yet, but I think as we move towards density estimation, that's going to be more critical. So at this point, it's like, okay, can we detect the animals? Yes, we can. How should we fly the gliders to best detect the animals? But I didn't go in density estimation. I was like planning to talk about that in my talk, and I was recording it. I was like, okay, this is going to be 7 hours long. Like, it's not going to work. I did get a detection function for fin whales from that same experiment that I was showing. And it varies more than anything with the glider's noise levels from the glider's flow noise. Okay. So looking at, and we were staying in a generally relatively small area, but if we were to take that detection function we got from that experiment would not be applicable to go survey all of Southern California, because as you moved into deeper water or different oceanographic conditions, I think that would really come into play. So yeah, I don't know the answer yet, or I just know that we should probably be doing that, and will be hopefully in the near future.
Would you be happy to share the uncut version of your talk then?
Yeah, I can. Well, the paper that I'm talking about, I've like just actually requested a extension on my revisions because I instead was having fun doing this webinar. So hopefully in the next couple of months too, then I'll be able to give that to you. But yeah, it was, I'll send you my whole dissertation talk, and then you can hear all about it.
I'm looking forward to this paper, clearly. Just about how detection range may vary with the oceanographic conditions. Just don't forget that the glider is measuring oceanographic conditions. So as the further you survey your area, the more you know what the propagation conditions will be. And then the acoustic propagation model and specialists, they exist, they know how to do this. So we have everything to solve this question. We need time. And yeah, mostly time, I'd say. I had a quick look when I was doing a survey on sperm whales, and my views. So Mediterranean Sea sperm whales seemed like stratification there was not varying enough to have any importance on short distance propagation questions. But as soon as you look at more lower frequency sounds, the big whales, fin whales, there will be a great difference based on the stratification or the sound speed profile. But yeah, the good thing again is that gliders do provide this. Everything is here to try and work on better estimating the detection range.
Pierre, exactly like you said, we just don't have time. I sort of feel guilty that we're collecting all this like really fine scale sound speed profiles for regions that it's not being collected in, and I've done nothing with it. So in time, right? We'll get there eventually.
Need more people to join the efforts together. Yeah, no, it's different. It's definitely big adventures of the gliders as well to have all the oceanographic data at the same time. Like even besides like this kind of noise propagation models, I think for habitat models having the in situ conditions, like it's always better. Like it's the best we could get. No, it's really cool. I was I don't know if Fiona, do you have something else to ask or? because I had just a random question popping up in my head, but it's a bit unrelated to the rest. So if you have a more serious question before I go ahead.
Well, my question isn't very technical, but have you ever noticed the animals reacting to these? Because obviously there's very little noise and they move through the water column, but maybe they're in the deeper waters. So have you ever seen an interaction or seen how they react or anything like that?
So I have I got given a little snippet of data when I started my PhD, but it's not long enough to do anything with. It's only like 30 minutes of a glider off of Australia. So I was just exploring it, but it's actually really cool because you hear the humpback coming closer to the glider, and then you start to hear a banging against the glider. And so the humpback, we think, is basically ramming it. And then about a day later, they had to go pick the glider up. So we think, we don't know why the humpback was doing what it was doing, but that's the only sort of like notable observation that I got.
Yeah, I was wondering as well, because when I got the data back from the first glider mission we run on the Sea Monitor, I have so many dolphins detection in there, like nothing compared to what I had on the vessel survey the same week or on the static receiver. So I was like, are they actually playing with the thing, or what are they doing? I don't know.
I do think that's kind of an interesting question, because if you're going to survey for like population abundance, I don't know how we would ever figure out, did the dolphins enjoy playing with it, but it is an interesting factor to keep in mind, because if you're just going to attract them all to your glider, then you're just going to have huge populations of dolphins everywhere.
Yeah. Yeah, I was gonna ask, I suppose I can ask it now because it kind of fits in the same. I have to ask this question because we had an episode on drones earlier in the seasons, and it was act and we had very funny story. Do you have funny fieldwork stories about gliders not behaving the way they should, or like not coming back to where they should come back, or anything weird happening with them?
Of course. Yeah, well, when you plan a mission, you already draw nice straight lines and say, I'm going to deploy here and recover there. And as far as I know, nobody nowhere ever did what was planned. Gliders are, I mean, they are slow. They're not very powerful to fight with currents. So as soon as anything goes wrong, your glider will be washed away by the currents. I don't have any fantastically exciting story. We had one glider that disappeared for several days, I think. We thought it was lost and just popped back at the surface, and the data then showed that it stayed under the water for all this time. No information on why or what it was doing. So either stuck on the bottom or trapped in fishing lines or something like this, but just came back up and then kept going on his mission as if nothing had happened. I think that's the most unexpected one.
And what a nice outcome.
Yeah.
Sorry?
A nice outcome in the end.
Yes, yeah,
all that stress, and then that we had sort of a similar one to that. I mean, yeah, like you said, the currents right now, Pierre, as I was listening to your talk, and I know how slow we're supposed to fly them to like get the best acoustic data, but we're battling these sort of crazy currents in Hawaii right now. And every time I have to increase, you can increase the glider's thrust to make it fly faster, and it's like making no forward progress. And so I'm increasing the thrust, but I'm like, oh, but I'm ruining all my low frequency recordings. Like, so there's that trade-off. But the project is focused on odontocetes, so it should be okay. But it's sort of like back in the day when I didn't know that was an issue, it didn't like kill me as much to have to increase the speed to deal with the currents, and now it's sort of devastating. But we had an instance where we had a glider that was the fin whale work. We deployed it on top of a US Navy array of hydrophones in Southern California. So they have this awesome multi-million-dollar array of 100 cabled hydrophones. And the point was then we could really accurately compare, but we could only fly between Christmas and New Year's because that's when the Navy was like on holiday. So we deployed right before Christmas. I went home to my family for Christmas, and we were picking up on like January 4th. There was a crazy storm. It snowed in Oregon. Our flights got canceled. It was this whole like crazy trying to get down there to recover them, but we had to get them off of this Navy range before Monday, because then all the Navy ships, they come out and do like training and stuff. and we couldn't have our device flying around out there when they were going to do all their training. So it was this sort of absolutely whirlwind, crazy attempt to drive down from LA, this whole thing to get there in the middle of the night. And then we drove 150 nautical miles off. And the glider wasn't communicating great because of the storm. But then we like got to where we thought it would be, and there it was, just like waiting for us. And it was like this miracle. And then we just turned around and headed back. But it's a lot of like stress and drama, and then it surfaces again, and you're like, okay, now it's fine. It's still alive.
You're really happy in this case when you're going to look back for them that they're yellow or very bright colors. I remember going back for one, it was like, oh, it's there.
Exactly. I don't think that will ever get old, because it's always this fear that, and I mean, right? You put anything over the side of the boat and you should just assume you're never getting it back. And so I hope that novelty of getting it back doesn't ever wear off, because it's always a little nerve-wracking.
Yeah.
For sure.
Okay. Well, we've been an hour and 20 minutes. Maybe we can wrap up. I don't know. Unless you guys have questions as well. I don't know. Feel free to. No pressure. You don't have to either.
I actually have a question for you, Pierre. So you were talking about you have traditionally used the altimeter on the deep gliders. Do you still do that, or was that early deployments? We typically don't do it, and so I always sort of have this fear of hitting the bottom if we're in anything less than 1,000 meters. But we don't run it to try and not add any noise. So what do you do with that these days?
Yeah, we, as soon as the bathymetry is known enough, then you can give the bathymetry information to the glider, and you don't need the altimeter. I don't know where this particular sample came from, but when we do cross slope surveys, when we go back to shallow waters on the shelf, then we turn the altimeter on only in uncertain regions. But as soon as we can, we turn it off to avoid. Well, it's a battery issue. It's not for the acoustics. Most of the things that are, I mean, UEA, the glider group, they have years of experience in piloting their gliders, and everything they do for battery saving actually works well for acoustics too. So being slow, turning off everything you can as soon as you can, that's good for acoustics, but that wasn't the plan. So yes, we use the altimeter only when needed. Sometimes you have to hit the bottom once to know you needed the altimeter, and then you turn it off. It's trial and error.
Yeah, we just sort of do this, I don't know, we just really err on the side of caution. And I mean, we use like Google Earth and bathymetry maps, which aren't perfect at the scale we're looking at. But if we know we're entering, if it's going to be shallower, we'll just like, okay, well, I guess we're only diving to 800 meters now. But if you're not finding that the altimeter is really taking away from the acoustic data that much, then that's probably the safer option for us to be using.
Yeah, it's clearly not that bad. I mean, if you have a automatic detection of clicks, then yes, that will trigger it. Otherwise, if you're using your eyes or your hands to analyze your data, you will see the clicks. They're obvious. They're impossible to miss. You can't mistake them for anything else. They're so loud, so predictable, and also you have the log files. So just read your log files, and you have the flag on each altimeter click. So it's
not easy to remove.
Yes, I think the easiest way to filter out all noise on your data is to go to the log files and know when there's noise, remove the sample, and you never see it anymore. So you may miss some interesting sounds that are only half masked by these platform noise. But if you want a clean bit of recording, that's very, very efficient.
Yeah.
Sure. Well, super. Well, I think we can. I don't know, unless you still want to add something. It's Friday. Well, first of all, we did mention that earlier, but we managed to make an episode with people a bit everywhere around the world. But I was going to say we're going to wrap it up because it's Friday evening and maybe people want to finish the week, but it's still not finished for everyone there. But
You
no,
guys
it
are
just
doing this was like a happy hour version, right? That they
yeah.
Yeah.
We're gonna look at what works the best. No, but just wanted to thank you all three again. It was like very nice working with you. Very nice team. Super interesting talks, and yeah, I'm so happy you contributed. It was super cool. Well, thank you to everyone.
Well, thank you for organizing this in the middle of the ends of your PhDs. That's quite brave. Hope
Thank
you'll
you.
have time now to recover, go in the field, and get rid of your dissertations.
Gonna plan my next glider mission. That's what I'm gonna do.
Good.
Yeah, I don't know if you, Fiona, you
Thank
want
you.
to wrap it up?
Yeah, just
Or...
thank you as well. I learned a lot for sure. So thank you to all three of you for your excellent talks. This is actually our last episode for this academic year. As Morgan mentioned, we'll be taking a break during the fieldwork season, but we will be back in September with more marine mammal research webinars, and we already have some great topics planned, so make sure to subscribe to our YouTube channel and our email alerts so that you don't miss any episodes that are coming up. As always, this and all our previous webinars will remain on YouTube in case you missed the live events. And just a big thank you to everyone who has participated in our webinars so far, so both the speakers and the viewers. And we're just very excited to come back in September again.
Yeah. And just a little note, if you're watching this later and the webinar is already passed, but you have questions, still ask them and we will try to pass them on to the speakers and see if they can answer. Yeah.
Absolutely.
Yeah. Thank you, everyone.
All right.
All right.
Thanks,
thank
everyone.
you guys.
Bye.
Bye.
Bye. Have a nice weekend.
Bye.